All right, here we go. First lesson I'm posting for Calc BC, and coincidentally, the last lesson of the year. So we almost cut through it all before coronavirus shelter in place. So, anyways, we'll keep going. This lesson is really just kind of a summary of our this last kind of small unit, which was a continuation of Unit 8. So we're just talking a little more about series, specifically converging, diverging. And so we've added a bunch of different tests. So I'm just going to talk about those right now. Not a whole lot to write down in the front. Front's just kind of a nice reference. We have the Nth Term Test, which is this basic idea that terms have to go to 0 to converge to even have a shot to converge. It doesn't guarantee it. It's a test for divergence. Rarely does it give us a conclusive answer, but when it does, I feel like it's worth using. I usually do it in my head, and if it's inconclusive, I just skip writing it. Geometric series we've been studying since the last chapter. So the R value, the common ratio, if its absolute value is less than 1, then it will converge. And we use that idea on the ratio test next too. And that's the only one that I'm asking for the sum of in Calc BC. So we have the ratio test, which is based off this idea that every subsequent term, there should be a +1, little typo there. Every subsequent term should be smaller than the previous term as we go to infinity. And we take the absolute values because we don't want to consider alternating series where negative term is always smaller than the next positive term or whatever. It approaches some L value as we take a limit. If that's less than 1, it converges for sure. If it's greater than 1, diverges for sure. It equals 1, it's inconclusive, which is going to happen at endpoints for power series. And so this doesn't tell you what it converges to, but just whether it'll converge or diverge. For power series, we use it a lot to find interval of convergence, radius of convergence. Most of these tests we're using a number series where there's no x values. P series test, special case, comes up a lot. You have 1 over n to a power. P is the power. If the p value is greater than 1 and it's in the denominator, so if we treat it as positive when it's in the denominator, if it's bigger than 1, it converges. If it's equal to 1, that's a harmonic series, it diverges. If it's less than 1, it's going to diverge for sure. So use that one whenever possible. Alternating series tests, a lot of the series that we've encountered over the last month or so have been alternating, and they converge easier than non-alternating series tests. And so if we take the limit and they go to 0, then it for sure converges. It looks like the nth term test, but it is not. It's only applied to alternating series. So the integral test is based off this idea of sort of looking at a series and the partial sums kind of looking like almost like a Riemann sum approximation for the area under a curve. And if we integrate that curve to infinity as an improper integral and it converges, then ours will converge also. If it diverges, ours will diverge also. We proved that in class, went into detail with that. So that's how I think we sort of figured out our P series test, a special case of that. It's, comparison test is definitely like last resort because it's the least straightforward and requires you to know another series different than the series you're looking at that will for sure converge, and that yours is able to be compared to and smaller than all the terms, term for term, then yours would converge also. So if yours is smaller than all the corresponding terms, it doesn't have to be the whole thing, but starting at some point, then yours will converge. Same thing if you can find a series where you know it diverges for sure, and you know that all your terms are bigger than those terms or equal to them, then yours is going to diverge also. But that one's a little harder to execute. The idea makes sense, I think, simple enough logically to feel comfortable with, but pulling it off is a little harder. So if we can use any other test, probably going to be better. I don't know. Absolute convergence is this idea that a lot of the series we see have positives and negatives. And some of the tests that we have here only work, the integral test is supposed to be for a series that's all positive terms. And so you can't really use it for an alternating test. It's not going to be a continuous function. But we can force all terms to be positive, perform the test. If that case converges, that's worse than if there's some negative terms. The negatives and the positive terms will kind of cancel each other out, and you'll converge quicker to a smaller number. But if you force all the terms to be positive and that converges, well, then the ones with some negatives in it and whatever will converge also. So, and if that happens, we say that a term converges absolutely. If it doesn't work, that you force them all to be positive and it diverges, but the original one still converges, we call that conditional, converges conditionally, conditional convergence. So when it doesn't converge absolutely, but it still converges. We learned one new error approximation that works for alternating series. And it's kind of a simple one. And it just says that for the nth partial sum, the error will be less than the next term in the series. So pretty easy to execute, and it's a lot easier than Lagrange error bound. So you should probably want to use it whenever possible. Anyways, that's a quick rundown. Whenever we can, if it's a geometric series, use geometric series test. If it's P series, use P series test. If it's alternating series, use alternating series test. Those are all very specific to certain kinds of series. And probably the quickest way if you can identify those series. Otherwise, you can try the other ones. But so on the back, I have a few examples here. And I guess I'm just trying to focus on getting a little more practice with the integral test. But I can mention the other tests that seem appropriate at the same time. So, these are all number series on the back. So we're not looking at intervals of convergence. We're just looking at, we should get a converges or diverges answer, one or the other. We could try, nth term test real quick. Nth term test. And that would be the limit as n goes to infinity of natural log of n over n. Now, if we just plug those in, we're getting infinity over infinity, which is indeterminate. We can use L'Hopital's rule. I'm okay with you guys being a little lazy and, saying, well, which term is getting bigger than the other? Now, this is a linear function, which grows like that, which keeps getting bigger and bigger. It's level 1. Natural log looks like this. What happens is it goes to infinity, but its slope is getting less and less steep. So this one is going to keep getting bigger. It's going to get bigger than this one. So this is going to dominate, and it's going to go to 0, which is inconclusive. But and, I guess we could try a ratio test. Again, like I said, the point of these was to practice the integral test, but maybe we'll realize that these other tests aren't helping us out a whole lot. So ratio test, limit as n goes to infinity, absolute value, natural log of n plus 1 over n plus 1 divided by the nth term. And we can't simplify anything here. But I usually look at the corresponding terms, I take the limit, dominant terms, that's going to 1. These are really close to each other, so they're going to 1. And it goes to 1, which is inconclusive. So anyways, all that effort didn't really get us anywhere. So what I would try next, this is definitely not, this is not a geometric series. This is not an alternating series. It's not a P series. So all those tests are out. So probably the next one to try on the list would be an integral test. Integral test. Now, let's take a look at the requirements of integral test. One, it says that the terms need to all be positive, which, I just graph these up here. And the denominators, if we're starting at n equals 2, the denominator is always positive. This point is 1, 0. So starting at 2, these are all positive. And even if we started at, say, something where we got some of these negative terms at the beginning, that's fine. The rule that it has to be positive, all the terms have to be positive, is at some point and then go into infinity. So, but it is, all the terms are positive. And is it decreasing? Well, we talked about, I could, not that you necessarily need to show this, but decreasing would mean that the derivative was negative, right? Decreasing, negative derivative. So we would take the derivative of this, and this is bringing back some fun memories. Calc AB, derivative rules. This is probably use quotient rule. Now I'm going to put x's in here. I'm going to say low d high minus high d low all over low squared. Those funny ways of memorizing things that I generally resist and don't like, but whatever, works. So we get 1 minus natural log of x over x squared, and we want to know, when is it less than 0, or what are its signs? So we could figure out, we can say, the bottom's always going to be positive, right? Unless x equals 0. So we can't plug x equals 0 in there. And we can plug negative x's into this. So this function, just looking at like a number line, 0 is going to cause problems, and anything less than 0 is going to cause problems. So that's just outside the domain of this. And when x equals 1, the top equals 0. And this kind of goes back up to these graphs. And so between 0 and 1, this is negative. And when you're greater than 1, it's going to be positive. So actually, I'm sorry, I messed up. When x is, because we're subtracting this, when x is between 0 and 1, natural log of that value is negative, and you're subtracting it, so that's positive. And over here, it's going to be negative. So here, it's decreasing. Now, at first, it's increasing. And for ours, we're starting n equals 2. But even if we started like n equals 1/2 or something like that, it'd be fine. In the short term, it's increasing. It's in the long term that it has to be decreasing. Sorry, you guys couldn't see that. Anyways, just making sure that those things are true before we start using something that wouldn't be appropriate. So the integral test, we're going to say 2 to infinity of natural log of x over x dx. So we're going to treat it like a continuous function. We're going to do an improper integral. Now, this one has some other fun Calc AB integration techniques. U substitution, right? Natural log of x, du equals 1 over x dx. That's perfect. So this is This is u du. So it's u squared over 2. So it's going to be, we're going to plug our expression for u in terms of x back in. And we're going 2 to infinity. So I'm going to just write the infinities in there. I think I mentioned this before. Technically, it's not great form. But, if we're being lazy. Now, natural log of infinity, well, that just keeps getting bigger and bigger squared. I mean, this is going to blow up. This is going to a nice number, but this whole thing is going to blow up. And so this diverges. And that means that the original series that we're comparing this to also diverges by the integral test. And that's probably your best bet on that one. Okay, try the next one. Now, the next one, if this were the next test, I'd be, oh, that's P series. And this is going to be your best, quickest way. P equals 3, which is greater than 1, which means it converges. Done. So, that's what I would do. And hopefully you guys are going to get to the point where you start to recognize these, and it's going to save you a lot of time in the future. Right now, I'm just trying them all, practicing them. Nth term test, limit. Now, if you do the P series test, I want you to write P equals, I want you to compare it to 1. So I know that you know that that's the condition. Limit, this goes to 0, which is good, but not enough to say for sure that it converges as inconclusive. We do ratio test. I have a bad feeling about it, but we'll see. 1 over n plus 1 to the third power times n cubed over 1 divided by the nth term. The dominant terms here are going to be n cubed and n cubed. That's going to go to 1. It's going to go to 1. It's inconclusive. All right. So I guess next test would be integral test. If you're really just going down the list, it's P series. It's definitely not geometric. It's not a alternating series, so you can't use those. So integral tests. So is this a continuous function, at least where we're looking at it? Yeah, when n equals 0, it's undefined, so it's not continuous there, but at least for where we're interested in, it's continuous. It's decreasing. It's positive. All right, so it's appropriate to use integral test without doing anything extra. So we're going to go 1 to infinity, 1 over x cubed dx. It might help to rewrite it like this. So you realize, oh yeah, this is power rule. Increase it by 1, divide by the new exponent. And maybe rewrite it. Negative 1 over 2x squared. Please don't move that 2 to the top when you're moving the bottom down. The 2 doesn't have a negative exponent. It stays where it's at. So what do we get? That's going to 0. This goes to 1/2, which is the value of this improper integral. And so it converges to 1/2. Our series doesn't converge to 1/2, but it converges because it's going to behave similar to this improper integral. So there you go, converged by the integral test. This one right here. Now, if you're getting good at this, you'd be like, oh, that's P series. And you might be like, P, where's doesn't it have to be into a power on the bottom? Well, this is into the 1/2. So if you're good at recognizing these, here's the fastest way to do it. P equals 1/2, which is great, which is less than 1, which is bad. And it diverges. If it's equal to or less than 1, then it diverges. So I need to see you compare it to 1 and so I know that it diverges. So that'd be the quickest way, P-series test. We could try the other ones. Nth term test, usually inconclusive. Limit as n goes to infinity of, and I don't, you write however you want. It's going to go to 0, which is good, but it's inconclusive. And we do ratio test. If you're looking for practice, limit as n goes to infinity of the absolute value of 1 over, we could do square root of n plus 1 times square root of n over 1. The dominant terms here are going to be square root of 1 and square root of n and square root of n. As we go to infinity, they're going to go to 1, so it's going to be 1, which is inconclusive. But you should be really good at ratio tests anyways. You have to do it for power series all the time. So I guess the next one we could try, if we're just going down the list, would be integral test. Definitely not a geometric series, definitely not alternating series. Inappropriate to use those tests. So integral test, is this a decreasing continuous positive function for n values of 1 to infinity? Yeah. It's always positive. Terms are getting smaller. That's what the nth term test already showed us. So it would be appropriate. Now, when we write this, we're going to put x's in because we're kind of trying to treat this like when the n values are in there, it's kind of a discrete type of thing. You're not plugging all the n values between the integers when you create all the terms in a series. So we're comparing it to this continuous version. Now, I would rewrite it like this and realize that this is a power rule. So increase it by 1, divide by the new exponent, multiply by the reciprocal if it's a fraction. So we're going to get that, and it diverges. So our series also diverges. So there you go. Just some more practice. Today's assignment, giving you a couple of worksheets, some multiple choice, some free response, which is, that's when these series tests on AP tests get a little more fun. Your upcoming test in my class won't have anything like that. It's just going to really be like assignment 9-3 kind of work. But we're gonna start looking at free response questions now, and you're going to get to answer them for sure on your practice test, because every year, one free response question out of the 6 on the AP test for Calc BC is going to be related to series, and those can be more difficult, especially at first. But I think you guys should be able to get to a point, if you work hard on this stuff, to start to see some of the, predictableness of most parts of them. So that's it.